So, good evening, everyone. Welcome to the solving session of Waste to Energy Conversion course instructed by Professor P. Mandal. I am from IIT Roorkee. I am one of the TA for this course. My name is Asma Parveen. I am a PhD scholar in Civil Engineering Department at IIT Kanpur. So, what we will do is first we will go through for the recap of the week 6 lectures. Then we'll solve the assignment questions, followed by one question based on the volume calculation of anaerobic digester. So first we will go through the module 1 of week 6. So first module was about anaerobic digestion. So what happens, these are the contents. In module 1, there is anaerobic digestion, then followed by mechanism of anaerobic digestion, then microorganisms for anaerobic digestion, then pathways for anaerobic digestion, and finally pre-treatment of lignocellulosic biomass and wastes. So first, we will see what are the feedstock we can feed for the anaerobic digestion and what are the products we get. So in anaerobic digestion, what happens that the organic matter which are present in the feedstock is degraded by microorganisms and converted into simpler products. And one of the end product of anaerobic digestion is biogas. And as we know, biogas has high calorific value. So these biogas can be used for cooking or or it can be used in any industry for combustion. So the other primary products of anaerobic digestion is hydrogen. We get biofertilizer. The digested sludge has high nutrient value and it can be used as a fertilizer or compost. And as we know, in anaerobic digestion, we apply the feedstock along with water. So we will get some water which we can reuse after treatment. So the important feedstock which we apply in anaerobic digestion is energy crops. We can apply animal waste like cow dung, or we can apply some industrial waste from breweries which have high organic matter. We can also apply MSW, municipal solid waste. And for anaerobic digestion, we can apply restaurant or food industrial waste, and also the sludge from wastewater treatment plant are digested anaerobically. So next, what is biogas? So biogas is basically a mixture of gases. It consists of methane. Methane is around 50 to 70%, followed by carbon dioxide, which is around 15 to 25%. Sorry. Carbon dioxide is around 25 to 50%, nitrogen is around 0 to 10%, followed by hydrogen 0 to 1%, hydrogen sulfide 0 to 3%, oxygen 0 to 1%. So the main component of biogas is methane and carbon dioxide. So methane has calorific value and we can use it for other purposes. So what happens is there are some microorganisms like bacteria which feed on the organic matter present in the feedstock, and due to different processes like due to hydrolysis and other processes, these organic matter are decomposed in simpler compounds and finally into methane gas and other gases in absence of oxygen. So these are some of the waste materials, and their average dry matter content is given. And out of that dry matter, how much biogas we can produce per kg of substrate, followed by what will be the methane content in the biogas. So first is wheat straws. In the average dry matter content of wheat straw is 86.5%. And the biomass potential is it can produce 367 liters per kg biogas per kg of substrate. And among these 367, we have 78.5% of methane content, and the rest part is the other gases like CO2, oxygen, or hydrogen. Next is barley straws. The average dry matter content of this is around 84%, and we can produce around 380 liters of biogas per kg of the substrate. So the methane content here is around 77%. Next is leucine. It is given to livestock as food. So the average dry matter content of leucine is around 22.5%, and its biogas potential is around 445 liters per kg of the substrate, and it has high methane content of 77.8%. And we can, in grasses, the average dry matter content is around 16%, and the biogas potential is around 557 liters per kg, and methane content is high, that is 84% of the total biogas produced. Then we have corn silage, it has 52% of methane content. Then we have corn stalks, and finally we have dried leaves. In dried leaves, the average dry matter content is 12.5%, and biogas potential is around 260 liters per kg of the substrate, and the methane content is around 58%. So here are some other waste like beet leaves. It has methane content of 84.8%. Then we have poultry waste, which comes from rearing of poultry. The average dry matter content is around 27.5%, and biogas potential is around 520 liters per kg, and methane content is around 68% in the biogas. Then we have cattle manure, horse dung, sheep dung, pig manure. Next, so these are the steps of anaerobic digestion. So what happens? The complex organic compounds like carbohydrate, fat, proteins are present, and if lignin is present in the feedstock, then there are some pre-treatments which are required to extract the cellulose and cellulose from this and then feed for anaerobic digestion. So what happens? The first step of anaerobic digestion is hydrolysis, in which the complex organic compounds are converted into simpler organic compounds. Like carbohydrates are converted to sugar, proteins are converted to amino acids and peptides, and fats are also converted to simpler organic compounds. Then after hydrolysis, what happens? That fermentative bacteria convert these simple organic compounds into short chain fatty acids, and this step is known as acidogenesis. Along with this, some amount of simple organic compounds are converted into acetic acid or acetate, and this step is known as acetogenesis. Also, some amount of hydrogen and CO2 are produced along with short chain fatty acid acetate. So these are produced by hydrogen producing these are produced by the some of the microorganisms present during acidogenesis. So after we have short chain fatty acid, then these can be converted into acetate by acetogenesis, or these can be converted into hydrogen or CO2 by hydrogen producing acidogenic bacteria. Then whatever acetate and hydrogen and CO2 are present, then these are converted by methane forming bacteria and methane and CO2 are produced. So this figure shows the quantitative description about how much of each component is produced from each step. So what happens? The organic compounds are first hydrolyzed and converted into short chain fatty acids. About 76% of the organic compounds are converted to short chain fatty acids, and around 4% are converted to hydrogen, and around 20% are converted to acetic acid. So, and among these 76% of short chain fatty acid, we get around 24% of hydrogen from this, and we get around 52% of acetic acid from these. Then what happens? These hydrogen can be converted to acetic acid or these hydrogen can directly to be converted to methane. So we can get methane from hydrogen or from acetic acid. So through hydrogen route, we get around 28% of the methane, and from acetic acid we get around 72% of the methane. So the first step shows hydrolysis, that is conversion of organic compound to short chain fatty acid, and acidogenesis. Uh, this is the conversion of organic compound to smaller acids. Then we have acidogenesis and dehydrogenation, in which acetic acid is produced, and finally we have methanogenesis, in which methane is produced. Next, here is an elementary description of anaerobic digestion, in which we say a chemical compound CnHaOBnC is converted anaerobically to methane, CO2, the CH5H7O2N is the bacterial biomass. Then we will have ammonium, we have carbonate. So it is a balanced equation which shows how 1 mole of this compound is digested anaerobically. So now here we have D equals to 4A plus 4N plus A minus 2B minus 3C, and S is the fraction of waste which will be converted into cells. Because in anaerobic digestion is taken place by microbes, so microorganisms will consume organic matter and their population will grow. So some fraction of the organic matter will be consumed for the microbe growth. So S is that fraction of waste which is converted into a biomass. Next, E is the fraction of waste which is converted into methane for energy. So S plus E will be 1, because some part of the organic matter or waste will be converted into biomass, and the rest will be used for converting into methane. And see, this is the empirical formula for the waste which is taken for this equation, and C5H7O2N is the empirical formula for the bacteria. Next, what are the factors which affect the biomass yield? First is solid dry matter content in feed waste. Generally, what happens, around 8% of total solids is applied in anaerobic digestion. So how much dry matter is present in feed waste and how much is the loading in the anaerobic digestion, that will determine what will be the biomass yield. Next is carbon to nitrogen ratio. So for growth of any organism, carbon is required, nitrogen is required, and other elements like phosphorus and some trace elements are also required. So for growth of the microorganism, some proper carbon to nitrogen ratio is required, and this ratio should be present in feed, and it will determine how much biomass is produced. Next is temperature. Generally for anaerobic digestion, high temperature is needed. What happens? Some reactors are run at the atmospheric temperature, and some are heated to increase the rate of degradation and fasten the digestion. Then next is the pH of the solution. The microbes which are working for converting the organic matter into methanes are very pH sensitive. Some microbes work in acidic pH, some work in neutral pH. So what is the pH of the solution will also determine how microbes are responding in that pH, and that will determine what will be the overall biomass yield. Next is retention time. So retention time is the time for which the feedstock or organic matter or waste is there in the anaerobic digester. So the retention time of the waste should be optimum, so that the complete conversion of organic matter is taking place inside the digester. Next is what type of digester we are using. Next are the microbes type. Next, so these are the group of biogas microbes. There are two group of biogas microbes. because along with methane, some other gases are also produced. So there will be some methane forming microbes and some non-methane forming microbes. So methane forming microbes are two, because we are getting methane from two ways. First from acetic acid and other from hydrogen and CO2. So one of the microbes is acetoclastic acetate degrading bacteria, that it will degrade acetate and produce methane. And next is hydrogen utilizing bacteria that will use hydrogen to produce methane. Next, we have non-methane forming bacteria, in which we hydrolyzing and fermenting bacteria, in which hydrolysis and fermentation of organic matters take place to produce simpler fatty acids and some and next is acetogenic bacteria, in which acetic acid or acetate is produced. So hydrolyzing and fermenting bacteria are of two types. First is the hydrolytic and next is the acetogenic bacteria. So among acetogenic bacteria, we have two types. First is the hydrogen producing acetogens that will produce hydrogen from acetate, and next is the homoacetogens. So we will see the role of microbes involved in the main three stages of biogas production. So the first stage of biogas production is fermentation, in which hydrolysis and fermentation of organic substances takes place. If the organic matter is cellulose, then cellulose decomposing bacteria will convert the cellulose into simpler molecules like monomers or oligomers or saccharides. Next, if there is protein in the matter, obviously there will be some protein, and these protein will be converted by protein decomposing bacteria into amino acids. And if there are fat, then fat will be degraded by fat decomposing bacteria into fatty acids and alcohol. And finally, the overall product will be short chain organic acid, aldehyde, hydrogen, and CO2. Next is the second stage, which is hydrogen producing acetogenic bacteria, which decomposes the substances, that is the organic acids, aldehyde, and others from the first stage to acetic acid, hydrogen, and CO2. And finally, the third step is the methane producing bacteria, which converts the substances or product from the produced from step 1 and step 2 to methane. So we can divide the overall process of anaerobic digestion into 3 steps. First step is the hydrolysis and fermentation. Next is the hydrogen and acetic acid production, and last is the methane production. So we will see what are the hydrolyzing and fermenting bacteria. So as I told you, the first step of fermentation of complex substance is the hydrolysis. In hydrolysis, the complex organic compounds are converted into simpler one. Like if we have carbohydrate, then these carbohydrate are polysaccharides, and that will be converted to oligosaccharides or monosaccharides. Proteins will be converted to peptides and amino acid, and we have some short of fat like triglycerides, then these will be converted to fatty acid and glycerol. And if there are nucleic acids, then these will be converted to hydrocyclic nitrogen compounds, ribose, and inorganic phosphate. So what happens, whatever complex substances are produced, they are decomposed into the simpler units of whatever they are made. So some of the anaerobes like streptococcus, bacillus, these are some of the anaerobes which are used for anaerobic digestion. So what happens, these bacteria uses some enzymes to like cellulose, hemicellulases, amylases, etc. to convert or depolymerize, because carbohydrate, lipids, and proteins are complex polymers, and these are converted by microorganisms by using enzymes to some soluble molecule. So if we have a carbohydrate, then carbohydrate will be converted into simpler units of sugar and alcohol. And if we have cellulose, then cellulose will also be converted to glucose and cellulose. As we know, carbohydrates are mainly made of sugars. So the simpler form we will get will sugar and alcohol, and similarly from cellulose we will get glucose and cellulose. Next is protein. Protein are made of amino acids. So through hydrolysis we will get amino acids, and through from peptides we will get fats or fatty acid or glycerol. And lignin. Lignin are generally not desirable in anaerobic digesters because their degradation is very slow. So we need some pre-treatment to first remove the lignin from the feedstock, and then apply, and then send the feedstock for anaerobic digestion. So some of the anaerobes like bacterioloids or lactobacillus, these act as acetogenic bacteria. These help in the hydrolysis of the organic matter, and sorry. So the hydrolysis product we will get from sugar, like we have from carbohydrate and glucose, sugar or and glucose are produced, and these sugar is further converted to simpler compounds like fatty acid or carbon dioxide and hydrogen. Alcohol is converted to fatty acid and carbon dioxide. Amino acid, ammonia, sulfide are converted to fatty acid, and glycerol are converted to acetate and carbon dioxide. Next is acetogenic bacteria. So acetogenic bacteria, the example of acetogenic bacteria are Clostridia and Acetovibrio. What happens? These bacteria convert the, like we have propionate, and these convert the propionate or alcohol into acetic acid. So the end product is acetic acid, carbon dioxide, and hydrogen. So there is one more route for production of acetic acid through hydrogen and CO2, and this is known as homoacetogens, which combine hydrogen and carbon dioxide to produce acetic acid and water. Next is the methanogenic bacteria. There is two ways or path through which methane is produced. First is from acetic acid, and these methanogens are known as acetoclastic methanogens. These convert acetic acid to methane and carbon dioxide. So around 70% of the methane is produced through this step. That is 70% of the methane is produced from acetic acid, but this step is highly sensitive and has the slowest growth rate. So the overall methane production will depend upon what is the growth rate of this reaction. So the limiting step or the limiting so the limiting reaction rate will be the conversion of acetic acid into methane. So next is hydrogenotropic methanogens. These convert hydrogen and carbon dioxide to methane and along with water. So around 30% of the methane is produced by this route, and they are less sensitive and have higher growth rate. So the rate limiting step in the methane production will be conversion of acetic acid to methane. That is, acetoclastic methanogens are most sensitive to the operating conditions, and they have the slowest growth rate. So formic acid or methanol can also be converted to methane by bacteria. Next is methanogenic bacteria. So methanogenic bacteria are anaerobes, that is, they perform under absence of oxygen. If oxygen will be present, then they will be then even a small amount of oxygen has very harmful effect on methanogens, and their growth rate will be retarded in presence of oxygen. So they are anaerobes, and and they are quite diverse in nature. So more than 10 different genres of methanogens have been described, but for production of methane, we need a complete anaerobic conditions. That is, oxygen should not be able to penetrate in our reactor. So methanogens are divided into groups by their ribosomal RNA and the substrate which are used for their growth. So these microbes are specific towards some substrate, like they will grow in presence of some very well in presence of some substrate. So these are used for to classify them into groups. So the group 1 contains the methanobacterium and methanobrevibacter, and group 3 contains the genus of Methanococcus, and group 3 contains several genera including Methanomicrobium and others. Next is pathway for fermentation. What happens is that pyruvate is produced from sugar as one of the intermediate step, which is further converted to acetate, fatty acid, carbon dioxide, and hydrogen. And at for hydrogen, at low pressure of hydrogen, acetate production is favored, and at high pressure, propionate, ethanol, lactate, and are favored. Next. So some pre-treatment is required for converting or for removing lignin present in biomass and waste. So there are three types of pre-treatment. First is physical pre-treatment. In physical pre-treatment is generally done by milling, in which biomass is shredded, and through this there is increase in accessible surface, but most of the methods are very high energy demanding. Next is irradiation, in which the biomass is exposed to some sort of radiation like microwave radiation. So because of this, there is removal of lignin, but along with there is decrease in cellulose. And most of the radiation cannot remove lignin. Next is other method like hydrothermal method, in which high temperature is used or pyrolysis. So due to this method, there is a decrease in degree of polymerization, but this method is not used for industrial applications. Next is chemical and physicochemical pre-treatments, in which first is the explosion, in which the biomass are exposed to CO2 and sulfur dioxide. Because of this, there is increase in accessible surface area. Next is alkalis like sodium hydroxide, NOH is used to delignify the waste. Next, we can chemically treat by using some sort of acid like sulfuric acid or hydrochloric acid. Next is we can use a gas like NO2 and SO2, or we can use some sort of oxidizing agent. So physicochemical or chemical pre-treatments are the most extensively effective and are most promising process for industrial applications. And these are used, but they require harsh conditions, because we are using acids very high high concentrated acids like sulfuric acid and HCl, and also we are using alkali, so the pH will be very high in case of using alkali, and will be very low when we are using pre-treatment using acid. Next, we have biological pre-treatment, in which some sort of microbes like fungi are used to delignify the waste. So the advantage of using biological pre-treatment is that the energy requirement is less. Also, there is no requirement of chemical, because lignin is converted to delignification takes place by some sort of fungi or microbe. So we do not require much energy, or we do not require any chemicals, but we need to provide the optimum conditions for these fungi and microbes to grow. So because of exposing the lignocellulosic biomass, there is a hydrolysis of lignin, and there is also reduction in polymerization of cellulose. But these are not considered for commercial applications because these fungi and microbes have some growth rate. They cannot perform above that rate. So their removal of lignin or delignification is limited. So we'll move to module 2, which was also
Madam,
on, yes.
Madam, I had a doubt. Why we have to remove the lignin?
Because lignin is not very complex polymer and it is not degraded easily. That's why we first have to remove the lignin so that whatever cellulose or proteins are present in the waste, we can digest it.
Oh, fine, ma'am. And in some paper industries also, I have seen that there also the removal of lignin from the pulp.
Okay. Then they.
They're yes, yes, ma'am. They're using thermochemical. I think, ma'am. Their digestive process called they're adding sodium hydroxide to that, and so that some reaction will go under high temperature also. Then
Okay.
later they'll wash the pulp and they'll go for further processing.
Yes, because we need to remove the lignin, otherwise the microbes will not be able to consume the organic matter. That's why lignin is first removed. And also you're saying about temperature. Generally, anaerobic digestion takes place in thermophilic or mesophilic range. For thermophilic, we need to increase the temperature so the digestion rate will increase. But to increase the temperature, we have to apply external heating. Um,
And ma'am, in we don't have any anaerobic microorganism to digest the lignocellulosic biomass also.
I don't have idea about this.
Okay,
Okay.
okay, madam.
Okay. So we'll move to module part. So we'll discuss about the type of the anaerobic digestion process, what is the kinetics of methane formation, followed by some of the operation of the digester. And there are two types of anaerobic digester. We will discuss about that and what are the impurities present in the biogas and how they impact. And finally, how to calculate the sludge volume in a digester. So here is a flow sheet of anaerobic digestion of waste. So what happens? Organic feed. First, if we have some sort of waste, we will shred it, blend. We will break into smaller particles. We will blend it, and for anaerobic digestion, if the organic feed is dry, then we need to add water, and then some chemicals are added for pH adjustment because generally the anaerobic digesters run in the neutral pH between 7 to 7.5. So we need to add some chemicals and adjust the pH. Followed by, if there is lignin, then we need to do some pre-treatment of feed. And finally, these are applied into anaerobic digesters, which can run in the mesophilic temperature range or thermophilic temperature range. So mesophilic temperature range is around 20 to 45 degrees centigrade, and thermophilic is in the range of 40 to 80 degrees centigrade. And after digestion, some gas will be produced. It will be mixture of others also. So from this mixed gas, we need to separate the methane. So methane is separated. There will be other gases, like there will be some sort of acid. There will be CO2, H2S, hydrogen, and there will also be some water. And after the separation of the gas, we will have solids. Along with, we will have some supernatant, which will be water. So the digester effluent is first dewatered. Water is removed from this these solids, and the digested solids is biosludge, and these can be either sent for disposal or these can be used as compost in agriculture. Then after dewatering, we will get water which needs to be treated, and after treatment they can be discharged or they can be reused. So next we will move forward. So here is a type of anaerobic digestion. It can be dry or wet. depending upon what is the total solid contents we are applied in the reactor. So in dry anaerobic digestion, the total solid content is around 25 to 45%, and in wet it is around 2 to 15%. In dry anaerobic digestion, the reactor volume required is less. It is a simple process. It is simple to separate the solid and liquid. It is more improved in terms of energy balance. It is more economical, and also the retention time required in dry anaerobic digester is less than the wet anaerobic digesters. Next. Next, we have the kinetics of methane production. So to produce methane, there are basically three steps. First was the fermentation or hydrolysis, followed by acetogenesis or acetogenesis and acidogenesis, and finally methanogenesis. Out of all these steps, normally methanogenesis is the rate limiting step, because as we have seen that conversion of acetic acid to methane is very slow. So that step will be the rate limiting step. But if cellulose content is higher in feedstock, then as we know, cellulose is a complex polymer, so its degradation will take time. So the hydrolysis will be the rate limiting step if cellulose content is higher in the feedstock. And if lignin is present, then it further decreases the rate of the hydrolysis. Sometimes transfer of the gaseous product to the gaseous phase may also be the rate limiting step, because whatever gas is produced that will be in the supernatant, and that gas has to go from the liquid phase to the gas phase, and it can be a rate limiting step. So next is the how we find the how much substrate is converted to biogas. So we can use this formula where R is the substrate converted per liquid volume, and S naught is the initial substrate concentration in the feed. Mu max is the maximum specific growth rate. It is the maximum growth rate of the microorganisms. Then theta is the hydraulic retention time, which is the time for which these waste is there in the digester, minus Ks, where Ks is the saturation constant. It is basically the substrate concentration at which the specific growth rate is half. And we know S naught, mu max, theta, and Ks. We can feed these in this equation, and we will get the substrate converted per liquid volume. So at around 30 to 37 degrees centigrade, optimum conversion of glucose can be achieved at a hydraulic retention time of 4 hours and 4 days in the acid and methane phase reactors. So here we can see that 4 hours is required for in acid phase reactors, and around 4 days is required for methane phase. So time required in methane phase reactors is much more than that in acid phase reactors, as the methane production is the rate limiting step. So for cellulose, if cellulose will be present in the feed, then obviously we have to increase the hydraulic retention time. So about 1 to 2 days is required for acid phase digestion, and around 5 to 8 days are required for methane phase digestion. So these are the kinetic constant given for glucose and cellulose for acidogenesis for acid phase, and for methanogenesis and methane phase. So here we have mu max, Ks, and mu max by 2. These three are the kinetic constants which we need to know to find the growth rate, to find the substrate conversion rate. So some of the important facts is that, first, methane fermentation at thermophilic temperature increases the methane production rate, because with increase in temperature, the activity of microbes increases. Because of that, the biogas production increases. Next is the pressure reduction may or may not provide the benefit of increase in methane production. So, and next is low pH and short retention time precludes growth of methanogenic bacteria. So methanogenic bacteria generally work in the neutral pH. So if pH will be low and their growth rate is also very slow, so if retention time will be less, then these bacteria will not grow properly and we will get less methane production. So there should be optimum pH and optimum hydraulic retention time inside the digester for the methanogenic bacteria to grow. Next is agitation. The continuous or rapid agitation may not be required in digester, and in some case it may be harmful and it can reduce the biogas yield. Next is the specific methane yield is directly proportional to biodegradable COD. So COD, that is chemical oxygen demand, it consists of all the organic matter and it can be of two types. It composed of biodegradable organic matter or it can be non-biodegradable organic matter. So what is the amount of biodegradable organic matter that will determine how much will be the methane, because bacteria can consume the or microbes can consume the biodegradable portion only and convert it into methane. So these biodegradable COD are also indicated in terms of volatile solids uh, in the digester. Next, here is a here is a figure showing the view of the digester. What happens? There is a substrate flow, substrate is applied. Then there is a small mixing zone in which mixing is done through, can be done through applying some gas or by mechanical mixing. Then there is sludge zone, and then there is fluid zone, and that is the supernatant, and there is a solid liquid separator, and at the top we have the biogas, and that is taken out from the reactor. And the supernatant, that is the liquid, is also taken from the top, and from the bottom we can get the digested sludge. So next is mixing. So we need little or small amount of mixing to reduce the natural stress stratification, because the feedstock will consist of water and the waste. So there may be chances that the water comes at the top and waste goes at the bottom. So little mixing is required to reduce the stratification. Next, mixing can be done by using some gas mixers, or can mechanical stirrers or mixers can be used for the mixing. Next, we can have different types of cover on the digesters. We can have fixed cover, or we can have floating cover, or we can have gas holding covers. So most of the municipal digesters are floating covers. These covers floats on the liquid on the supernatant, that is liquid part of the inside the digester. But floating covers are more expensive than fixed cover, and the normal or standard diameter range for these floating covers are between 15 to 125 feet. Next is rate. What is the loading rate of the organic matter? There are two types of digesters. First is low rate or conventional digesters. Next is high rate digesters. So in low rate digesters, the feeding rate is 0.5 to 1.5 kg volatile solids per meter cube per day. Whereas in high digesters, the feeding rate is 1.6 to 6.4. It is much higher than the low rate digester. Also in high rate digesters, the detention time is less as compared to lower conventional rate digesters. High rate digesters, continuous mixing is applied because the loading rate is very high and we have lesser detention time. So for the homogenization of the inside the digester, there is some sort of mixing taking place in high rate digester. In low rate, we apply intermittent mixing and sludge feeding. What happens in low rate? We apply the sludge, we do the mixing, we give everything, and we just keep the reactor to digest it. And after the detention time is over, we take out the sludge and we take out the supernatant. But the high rate digester works in continuous mode, or it can also work in intermittent mode. Next is most of the digesters are heated and operated in mesophilic range and are generally made of concrete or steel. So temperature has a very high impact on the growth of microbes. So for the optimum growth of microbes, sometimes heating may be required to bring the to work to make the microbes work in the mesophilic or thermophilic range. Next is what are the conditions inside the digester. So most digester works in the temperature range of 30 to 38 degrees centigrade, and the gas which is produced from the which comes out from the um, digester, the part of it can be used for heating of the digester. Next is optimum pH. It is around 7.7 to 7.2. Sorry. pH can be added pH can be maintained by adding acid or base depending on the conditions. And next is this pH is maintained by adding a by adding fresh sludge and not extensively withdrawing sludge. Withdrawing sludge are the sludge from which water has been extracted. So fresh sludge is added to maintain the pH in the range. Or we can maintain the pH of 7 to 7.2 by adding some sort of lime or some other base. Next is heavy metals. Heavy metals inhibit digestion because microbes, almost all the organisms require some of the heavy metals in very trace amount. So if heavy metals will be high in concentration, then the growth of microbes will be inhibited. So heavy metals must be removed before feeding in the digester. Next is the supernatant liquor which comes out from the digester. So the COD and BOD of the digester can be very high, and the supernatant liquid must be treated before disposal. What happens in municipal wastewater plants? There are anaerobic digesters to digest the sludge produced from primary sedimentation tank and secondary sedimentation tank. And whatever supernatant is produced from the digesters, these are sent back to the at the starting of the plant into primary clarifiers, or these can be sent to the grid chamber. Next is a two-step digester. So what happens ki acidogenic bacteria works better in acidic pH of 5.5 to 5.9. And we know that methanogenic bacteria work in the neutral pH of 7.4 to 7.9. So to provide optimum pH for both these, there are separate reactors are used. In first reactor, acidogenesis takes place and the pH is acidic. And the effluent or mixed liquor from this reactor is sent to the second reactor, in which methanogenesis takes place and pH is neutral, is between 7.4 to 7.9 in these reactors. So this is a schematic diagram of two-phase digestion model. In first, this is the acid reactor in which feed is applied, and some gas will also be produced in this reactor, which is taken out. And then there is a separator which separates the waste solid, and the liquid is sent to the methane reactor in which gas is produced. And then there is a separator in which waste solid is taken out, and these solids can be used for other purposes, or it can be disposed. And also from the separator, solids is separated and effluent will be the liquid part. And this liquor can be recirculated back to the methane reactor to get the for neutralization, and also to recover the methanogens from these, and again some part of the sludge or the digested sludge is recycled back to get the microbes in the reactor. And also in acid reaction, there will be some recirculation of the solids to get the acidogens bacteria. Next is two-stage anaerobic digestion. So in first stage, the main reactions which takes place is the liquefaction of organic solids, and digestion of soluble organic material. So the digester reactor we use for first stage is a high rate digester with fixed cover and continuous mixing. And for second stage or methanogenesis step, the main purpose is the supernatant separation. Then some gas will be produced, so gas storage and digested sludge storage. So the digester used for second stage is can be a conventional digester with low rate and with a floating cover and intermittent mixing. So the impurities which are present in the biogas and what are their impacts, we will see that first, there obviously water will be present in the water will be present in the biogas, and the water can react with H2S and ammonia or CO2 produced along with water and methane to form acids, and these can be corrosive to the reactor walls, and there is also chances of accumulation of water in pipes. Next is dust. If dust will be there, then it will cause clogging of compressor and gas storage tanks. Then H2S also will be corrosive, and it has very pungent smell. So if exposed to atmosphere, it will give very pungent egg rotten smell. So it is very toxic and it remains in the biogas. Next is CO2. CO2 is also impurity, so because it is a very low calorific value, and also it also causes global warming. So there will be siloxanes, there will be hydrocarbons, ammonia, oxygen, chloride, fluoride. These are the impurities, and these need to be removed from the biogas. So these are some of the methods for removal of moisture from the biogas and their advantages, and what is the disadvantage is given. The first step is the condensation method. So what happens in this method, along with moisture, higher hydrocarbon, dust, and oil are removed. And in the next is demister. It is a simple technique and often used as a pre-treatment before other techniques. And some of the other methods are moisture traps. Silica gels are used to absorb the water. The next absorption is glycol and absorption with hygroscopic salts. These salts are hygroscopic, so they can trap moisture from the biogas. Next is sludge volume calculation. So how much volume is required for the digester? It is the function of two things. First is how much volume of fresh sludge is added daily, and next is what is the how much time the sludge is required to be stored. So the volume of digesting sludge in a digester is a function of volume of fresh sludge added daily and the volume of digested sludge produced daily and required digestion time. So batch experiments have shown that if supernatant is removed from a batch of digesting sludge as it is produced, so volume of remaining digested sludge versus digestion time is a parabolic function. And for parabolic function, the average volume of digesting sludge will be V1 minus 2 by 3 of V1 minus V2, where V1 is the volume of fresh sludge added and V2 is the volume of sludge produced daily. Next, so the total the volume of total sludge in the reactor is given as V average, that is average volume of digesting sludge, into TD. TD is the time required for digestion, plus V2, where V2 is the volume of digested sludge produced daily, into TS. T is the time produces for sludge storage. So now what happens normally is that the sludge volume normally occupies the bottom half of the digester and the supernatant liquor occupies the upper half of the digester. So the total digester volume VT will be 2 times of VS. That is, VS is the total sludge volume. Next, we'll go to design of the anaerobic digester. So Here is a digester shown in which waste or feedstock is applied. There are two stages, first reactor and then secondary reactor. We get the biomass or the sludge, digested sludge, then we get this gas. So the factors influencing the plant performance is first is the solid matter. Solid or what is the dry contained in the feed? What is the carbon to nitrogen ratio? Because nitrogen is very essential because all the amino acids, peptides, proteins are formed from nitrogen. So carbon to nitrogen ratio also decide what will be the performance of the plant, then temperature, pH, and retention time. So these we have seen earlier that what is the dry matter and methane content. So here is a plot showing the variation of biomass production rate with temperature. So for each waste, we can see that with increase in temperature, the biomass production has increased. So we can see at 8-degree temperature, there is a least biomass production. At 25-degree, the production has increased, and at 35-degree centigrade, the production is almost 2 times than the production at 8-degree centigrade. So here is a typical carbon to nitrogen ratio of some of the waste. So here is a dry rice straw. So dry rice straw has carbon to nitrogen ratio of 67:1. It was on weight basis of 42:0.3 to get, we divided the top with 0.3 to get the denominator as 1. So we get 67:1. For dry wheat straw, it is 87:1. For corn stalks, it is 53:1. For fallen leaves, it is 41:1, and so on. So some of the suitable conditions required for digestion is that the solid or dry matter content applied is 8% of the total feed applied. Then next is carbon to nitrogen ratio between 20:1 to 30:1 is optimum. The optimum temperature is between 25 to 35 degrees centigrade, and optimum pH is between 6.8 to 7.2, with the retention time between 60 to 90 days. So for mesophilic digestion, the retention time should be greater than 20 days. And for thermophilic, the retention time can be decreased. So here is a cross section of the digester. It consists of 4 parts. So the bottom part will be the sludge layer, where will store the sludge. It will be the sludge layer volume. VSL is the sludge layer volume. Then above that will be the active digestion volume, that is VD. Above that, there will be gas storage volume, VGST, and above that, there will be the gas collection volume, that is VCOL. So the total volume of digester will be sum of these volumes. So total volume will be the sum of sludge layer volume, active digestion volume, gas storage volume, and gas collection volume. So it was the cross section that what are the parts in the digester, and next is the dimensions. So we can see that the digester consists of a cylindrical middle portion with a top hemispherical and bottom has and a hemispherical surface as the bottom. So V1 is the volume of the top head. V2 is the volume of the bottom head. S1 is the surface area of top head. S2 is the surface area of bottom head. Then we have V3, volume of the cylindrical part. H is the height of this part. Then we have R1, radius of the top. R2, characteristic dia of the bottom head. Then we have H1 and H2 as the height of top head and bottom head. Then we have D, the diameter of the cylindrical portion, and so on. And all these dimensions can be related to D. D is the diameter of cylindrical cylindrical portion. So all these V1, V2, all these can be related to D, and we can see what are the relations. So there is difference between cross section and dimension. Cross section consists of what are the parts in the reactor, and in dimensions we can see what is the radius, height, and all. So for calculation of volume, we will use these, that the volume of gas collector can be less than or equal to 5% of the total volume. Volume of the sludge collector will be less than or equal to 15% of total volume. And VGST plus VD equals to 0.8 times the total volume. And then we can calculate VGST using this expression or this expression. And we will take we will get two values using these two formula. So whichever value will be higher, we will take that value as the volume here, and we will use that for further calculations. So for to find the what is the dimensions of the reactor, we will use these expression which are related to D, that is diameter of the cylindrical portion. Next here is a numerical. We will skip this and move forward. Next is microbial fuel cells. So in microbial fuel cells, what happens is we use microbes which consume on the organic matter applied and produces electrons and H plus, and because and these electrons and H plus are used to produce electricity. So in microbial fuel cells, for the chemical reaction, we are using microbial reaction, that is, we are using microbes, and in place of fuel, we provide organic load of wastewater. So a typical here is a fuel cell which consists of an anode, a cathode, and there is one proton exchange membrane through which proton goes from anode side to the cathode side. So a fuel cell consists of anodic and cathodic membrane. So a fuel cell consists of cathodic and anodic chamber separated by electrolyte, which allow the flow of proton but restrict the flow of electrons through it. Then hydrogen is sent is feed towards the anode side, and oxygen are fed towards the cathode side. So a catalyst at anode side causes the hydrogen atom to give electrons and proton. Basically, oxidation is taking place at anode, and at cathode electrode, what happens is a catalyst consumes hydrogen, proton, and electron to produce to produce H2O. So these protons can pass through the proton exchange membrane, and electrons are passed from anode side to the cathode side by using some external circuit which makes the current. Next, here is a picture showing the microbial fuel side. Left side is the anodic chamber and right side is the cathodic chamber. So in anodic chamber, what happens? Some organic matter CH2O, which symbolizes organic matter, is applied, and because of oxidation, it will be converted to CO2, and H plus and electrons will be produced. So H plus will go towards the cathodic side through some membrane, and electrons will be transported externally by some external circuit. And at the cathode electrode, hydrogen, H plus, oxygen, and electrons will be used, and H plus and oxygen will be reduced to H2O. So basically, at the anodic chamber, oxidation takes place, and at the cathodic chamber, reduction takes place. So here is a reaction showing towards the anodic electrode, and bottom one is towards the cathodic electrode. So there are two types of electron transfer mechanism. First one is indirect mechanism, and other one is direct transfer of electron. So in indirect transfer of electron, some external materials or mediators are added. So in microorganisms, during the oxidation of the oxidation of the organic matter, electrons are produced. And these electrons are taken by some mediators in the electrolyte, and these mediators take the electron to the anode, and transfer the electron to the anode, and from anode these electrons go to the cathode side. So it is this mechanism is indirect, where bacteria or cell is giving the electron to some mediator and it is transporting. And while in direct mechanism, what happens that overall the biomass or cell moves towards the anode, gives its electron to the anode, and from anode the electrons is carried towards the cathode. So it is direct electron transfer by the microbes itself. So there is a electrochemically active redox proteins such as cytochromes are present on the outer membrane of the microbes, which can transfer electrons directly to the anode. Next, we have proton transfer mechanism, in which H plus is produced by oxidation of the organic substance, and through a number of reaction chains, that first it is transported to one of the hydrolyzed ionic side, then it transfers the proton to next one, then by series of these transport, finally the H plus goes towards the cathodic chamber. So these are some of the materials which are used to make anode, cathode, proton exchange system or electrolyte catalyst. Next, we have microorganisms with different metabolic paths and electron transport system. So we can produce electrons and H plus by oxidative metabolism, by either by oxidation, or we can produce by fermentative metabolism, which takes place in absence of oxygen. So there can be direct and indirect transport of electrons in both these pathways. And these are some of the name of the microorganisms which takes part in direct or indirect transport of electrons. Next, these are some of the microorganisms, along with what substrate is used, what is the material used for anode, what is the current produced, what is the power produced, and these are taken from these research papers. So we'll move forward and we'll see the comparison between performance of a microbial fuel cell in pure and mixed culture. So if we are using pure culture, then it will be susceptible to contamination of the microbes by external bacteria, and that will be undesirable, and the performance of the overall MFC will get deteriorated by contamination. So even though pure culture have high electron transfer efficiency, but there is a very high risk of contamination of the MFCs by the undesirable bacteria. And for mixed bacterial cultures, they have the advantage that they are very resistant against the external disturbances. They have higher consumption rate and smaller substrate specificity, that they can consume different substrate and do their work, and the overall power output is high in mixed bacterial culture. So the parameters or factors which affect the MFC operation are electrode material, what electrode material is used in making the electrode, what is the pH, how pH is maintained in the reactor, and what is the electrolyte, what protein exchange system is used, what is the operating conditions in the anodic and cathodic chamber, what type and composition of the substrate will used. All these conditions will affect the microbes, and that will eventually affect the overall performance of the MFC. So next, these two are the formula to calculate the current and charge. So to calculate the current, we take the summation of current densities over the electrode surface, and to calculate the charge, we integrate the cell current over the time. Next is voltage and current calculations. These are the formulas which we will use next week to solve the numerical on MFC. So from Ohm's law, we know voltage is IR, where I is the current and R is the resistance, and cell power is given as V, voltage of the cell, into current, and and how much voltage will be produced will calculate by subtracting the overall losses taking place. So V cell is EC, which is electrode potential for the cathode, minus EA, electrode potential for the anode, minus these are the losses which takes place in the cell. So these needs to be subtracted and we will get what is the voltage produced. Alternatively, we can use E cell equals to EMF. We will put EC minus E as EMF. It is the open circuit voltage, minus these are the losses. We will subtract these and we will get the overall E cell. Next, what are the losses which takes place in MFC? So there will be ohmic losses due to the, then there will be the activation losses because of accumulation of gases at the surface interface between electrode and electrolyte. Then there will be bacterial metabolic losses, concentration losses, mass transfer through the membranes. And next, voltage loss due to pH difference between the cathodic and anodic chambers. So the types of MFCs and improvement efforts. So the MFC can be single chamber, it can be double chamber like this, or it can be a flat plate, membraneless MFC, or upflow MFC. So some of the efforts which are going on to improve the voltage and power generation in MFC are adding suitable metal ions and using metal reducing microorganisms. So if we are using metal ions, then we need metal reducing microorganisms to produce electrons. Next is doping of the catalyst on the electrode. Catalysts are used to enhance the efficiency. Next is increasing anode area and decreasing the electrode distance, that is distance between cathode and anode, using more efficient microorganisms and using more suitable oxidant in cathode. So we'll move towards the last module, that is fermentation. First part of fermentation is in week 5 and the rest, week 6, and the next part is in the week 7. So fermentation is a process which convert the sugar or acid or gases, that converts sugar to acid, gases, or alcohol. So what we can do, we have organic waste or biomass, we can gasify it, we can produce the syngas, and we can use this syngas to produce ethanol. Or what we can do is we can directly get the we can directly ferment this organic matter to produce ethanol and butanol. And ethanol can be used as a blend with gasoline. It can be used as 10% by total volume. So butanol can also be used in pure form, or it can be blended with gasoline. Next is fermentation and energy production. So fermentation is a series of chemical reactions for converting the sugar to ethanol in presence of some microorganisms which feed on sugar. So the ethanol and carbon dioxide are produced and sugar, that is the reactant or substrate, is consumed and we get ethanol and carbon dioxide. Here is a reaction to alcohol along with CO2. So the source of sugar can be some sugar crops, or it can be some starchy crops like potato, or it can be lignocellulosic biomass. So if 6 carbons are present in the sugar, then it is known as hexose. Glucose is one of the hexose, and if 5 carbons are present, then it is known as pentose. So these 5 carbons will form a 5-way carbon ring, and hexose will form a 6 carbon ring. So next is the production of ethanol from 3 different feedstocks. So we can use sugar crops or starchy crops or lignocellulosic biomass. If lignin is used, then some pre-processing is done, then fermentation is done, and during fermentation, what happens? That the fermented mash has 40 to 10% of the alcohol. So distillation distillation is used to produce around 95 to 96% of the alcohol, and after that dehydration is done to further remove the water from the alcohol, and we get around 99.5% of the ethanol. So same thing is written here, is that the ethanol concentration in the fermented mash can attain a level of only 4 to 10%, depending on the operating conditions and the strain of yeast used. And we can distillate that to produce around 95 to 96% of the ethanol, and again it can be dehydrated to produce 99.5% of the ethanol. So the pre-processing step, for if we have sugar crop, then sugar will be present and we can directly ferment it. If we have starchy crop, then we need to hydrolyze the starch to sugar and then we will ferment it. Or if we have lignocellulosic biomass, then we need to first extract the cellulose, then we have to hydrolyze the cellulose to sugar, and then we will do fermentation. So if for sugar crops, least pre-processing will be required, and for lignocellulosic biomass, maximum pre-processing will be required. So here is the step which shows the production of ethanol from starchy crops. So here is corn. It consists of center part is germ. It consists of bran, starch, and gluten. So first, cleaning and steeping of grains is done, through which wastewater will be produced. Next step is grinding, from which germ is extracted from the corn. Next is washing and filtering, in from which fiber is separated. And next is gluten separator, from which we get the gluten. And finally, whatever is left is converted, is starch, which is converted to sugar, and this process is known as cooking. And finally, the sugar produced is fermented, and we get CO2, and we get some alcohol, which is distillated and dehydrated, and we get the ethanol along with some glucose and wastewater. So these are the steps. So the previous process was the wet process, and next is the dry process, in which first cleaning is done, followed by milling, then liquefaction, and then saccharification, in which starch is converted to sugar, and then it is fermented, then it is distillated and dehydrated to produce ethanol. And after that, the co-product processing is done, and it is used for animal feed and other co-products. Next is production of ethanol from lignocellulosic biomass and waste. For lignin containing biomass, we need some pre-treatments. First will be drying and grinding, then slurry is formed, then pre-treatment of slurry is done to remove the lignin, then detoxification and hydrolysis is done to convert the cellulose to sugar, then fermentation is done, and finally the product is recovered. We will get ethanol, we will have some solid residue, and along with some wastewater. So the common lignocellulosic biomass are agriculture residues and agro waste, which will consist of leaves, stalks, strovers, seed pods. It will have lignin in it. Then we will have municipal solid waste, food waste, paper, sorted refuse. Then we will have forest biomass and waste. It will consist of softwood. It will consist of hardwood, dead trees, forest thinning, etc. Next is industrial waste. It will have chemical pulp and waste, water solid, or it can be whole plant, which will use grasses and aquatic plants. So here is a pre-treatment. So if we have a lignin containing biomass, it will have lignin, hemicellulose, and cellulose. So first pre-treatment is done, in which the cellulose is altered. We will have some hemicellulose, then we will have these are yellow parts are the lignin, and along with that some sugar is formed from the hemicellulose. So after pre-treatment, we will have altered cellulose and simple sugar from hemicellulose. These both are produced during the pre-treatment. Next, the pre-treatment efficiency. So pre-treatment efficiency will depend upon the total sugar yield and the energy consumption during the process to produce the sugar from the lignocellulose. So the energy overall efficiency is given as TSY, that is total soluble sugar yield upon total energy consumption during the pre-treatment. So the favorable characteristics of pre-treatment process are that the cellulose which we will get should have high digestibility so that we can ferment it easily. Then there should be no destruction of hemicellulose and cellulose. So if destruction of hemicellulose and cellulose will be minimum, then we will get high yield. Next is no or little degradation of sugar. So if sugar and sugar derivatives are already degraded in the pre-treatment, so it will affect the fermentation process and its yield. So there should not be any loss of sugar and production of minimum amount of toxic compounds, because these compounds need to be treated and it will consume some cost and capital for its treatment. Next is no requirement of biomass size reduction before pre-treatment, because for size reduction also some energy will be required and it will consume some capital. So next is capable of operating in reasonable size and moderate cost reactors. No production of solid waste residue, because if it is produced, then it needs to be treated and then disposed of. Effectiveness, it should be effective at low temperature. And then there should be very high recovery of carbohydrates and other compounds. And it should be the carbohydrate and cellulose which we are getting, they should be fermentation compatible. And next is high lignin recovery for conversion into valuable co-products. So if we are removing the lignin, so if we can recover the lignin, that it will also serve as a resource to produce other co-products. Next is minimum heat and power requirements. It will determine the overall cost of the pre-treatment, and that will determine how much capital is required and the overall capital of the process. Next is different types of pre-treatment techniques. There will be four types: physical, chemical, physico-chemical, and biological pre-treatment methods. So basically in physical method, cutting and grinding is done where the size is reduced so that the accessible surface area and the pore volume increases. Next is chemical treatment. In some acids like sulfuric acid and bases like NOH are used to delignify the waste and decrease the degree of polymerization and increase the exposed area, and the cellulose increase the exposed area for making the cellulose to be accessible by enzymes. Next is physicochemical treatments, in which it uses the conditions and compounds that affect the physical and chemical properties of biomass to increase the surface area of the biomass for enzyme accessibility. So if enzyme can surface area of the biomass are increased so that microbes can feed on them and consume them. Next is biological, which alters the structure of lignin and cellulose, and they separate the lignin from the lignocellulosic matrix. Also, since it is biological process pre-treatment, so it will have a slow rate, but it will not produce any toxic compounds. So we can use white rot, brown rot, and soft rock fungi. These fungi can be used for biological pre-treatment. Next is detoxification. Along with the fermentation, many byproducts will be produced, which must be removed to get the ethanol. Also, the byproducts which will be produced, these can be have harmful effect on the fermented microorganisms, and they can inhibit the growth and working of these microorganisms. So these inhibitors should be removed while they are produced during the fermentation. So these inhibitors are characterized into three major groups. These are aliphatic acid, furan derivatives, and phenolic compounds. So biological, physical, and chemical methods are used to remove these inhibitors. We can do chemical detoxification by using some chemicals like sodium sulfite or sodium dithionite or sodium borohydride. Next is hydrolysis. So the major portion of cellulose and hemicellulose are glucan and xylan. So digestibility of glucan and xylan will determine the yield of the overall um, so it will determine so the digestibility of glucan and xylan can be determined from the yield of their respective monomers and disaccharides. So we can find out the digestibility of glucan as amount of glucose in grams plus 1.053 into amount of cellubiose upon 1.111 into amount of glucose. Similarly, we can use this expression to find the digestibility of xylan. These 1.053 or 1.111, these are the hydration factors of these compounds, and we can find out the digestibility using these expressions. So next is total sugar conversion. We can calculate from what is the glucose yield and what is the xylose yield, and we can use this expression to find out the total sugar conversion. So next, so we'll next move towards the previous year assignment for this week. So I'll share my screen. So there are 10 questions and there is 2 numerical. So we will first see the first question. So in anaerobic digestion method, normally the dash is the rate limiting step. If cellulose content is higher in the feedstock, dash may be the rate limiting step. So I'll give you 2 minutes, just 2 or 1 minute, because we have only one participant. So you can write your answer in the chat box and then we can move forward. So the correct answer is D, that in anaerobic digestion, methanogenesis is the rate limiting step. And if cellulose content is there, then hydrolysis will be the rate limiting step. Sorry. So the next question is, the type of losses in microbial fuel cell caused by uneven depletion of reagents and electrolyte is called as ohmic losses, activation losses, bacterial metabolic losses, or concentration losses. So just write your answer in the chat box. So the the answer is D, that is concentration and losses. Next, we have third question. That is the theoretical substrate conversion rate per unit reactor volume can be estimated as. These are the formula. You just write which option is correct, A, B, C, or D. So right, the correct answer is B. Next is, which of the following has highest carbon to nitrogen ratio? Dry rice straw, dry wheat straw, corn stalks, or fallen leaves? So just write your answer in the chat box, or you can also unmute yourself, or you can say the answer.
Madam, your voice is not audible.
Sorry. So the correct answer for fourth is dry wheat straw, which has the highest carbon to nitrogen ratio. Next is question number 5, that identify the different zones in anaerobic digester. We have to identify which zone is A, B, and C. So I'll give you 1 minute so that you can write your answer. So C is the correct option. The bottom part, C is the mixing zone, then B is the sludge zone, and B is the sludge zone, and A is the fluid zone where there is supernatant. Next is identify A, B, and C in the fuel cell. So here is the diagram. We have to identify what is A, B, and what is C. So you can write your answer in the chat box and then we can move forward. So the correct answer is A. Left side is A is anode, B is the cathode, and C is the proton exchange membrane. Next question is the relation between total digester volume and total sludge volume is given by. We have to find out of these expression which is the correct expression to relate total digester volume and total sludge volume. So you can just write your answer in the chat box and we can start. So just write your answer in the chat box, then we will move forward.
Sorry, ma'am, already answer displayed, but actually I'm trying to check whether it is there or not.
Okay.
So, madam, can you explain this?
Yeah.
How we have got this answer?
Seventh one.
Yes.
Okay. So there was this is also a direct question from slide. It was that there was one statement saying that the total sludge volumes take around half of the reactor volume and the rest half is occupied by the supernatant, that is liquid. So the overall total digester volume is 2 times the total sludge volume, that is VT is 2 times VS.
Okay. Okay. Okay.
Okay.
I thought VD like that. Okay.
No, it is
Then,
VT and VS, relationship between total sludge volume and total digester volume.
so VD, ma'am.
Sorry.
VD.
Active volume of the reactor.
Okay, ma'am. Okay, here
So we
VD the active digestion volume.
active
Okay.
digestion volume. So here is the figure that VT is the active digestion volume and VT will be the total digester volume. So we have to find the relationship between VT, that is total digester volume, and what is the sludge volume. So I will show you, wait.
Okay.
So here is a point that the sludge volume normally occupies the bottom half of the digester and the supernatant liquor occupies the upper half. So the
Oh, right.
overall digester will be 2 times of the volume of the sludge.
Okay, okay, right, ma'am.
So next question is, the major portion of cellulose and hemicellulose are glucan and xylan respectively. Digestibility of both glucan and xylan can be determined from the yield of their respective monomers and disaccharides. The digestibility of xylane percent can be given as, we have to find the expression, that which expression will give us the uh, percentage of digestibility of xylan. So you can write your answer. So the correct expression is C. It is a direct question from the slide, so you can refer the slide for the formula.
No, ma'am, I have seen that it is 1 point on denominator is 1.136.
Sorry, let me check once.
In denominator, yes. Please check.
C is the correct option.
No, ma'am, the denominator is the factor is 1.136.
Okay, sorry, let me check once.
Yes.
वीडियो कॉल करेगा
I'm sorry, the correct option is D. Sorry for my mistake. So the digestibility of xylene is given by the last option. Next, we have a numerical. Calculate the volume of digester chamber required for the biogas production from the cow dung of 12 cows having body weight of 180 kg each. Assume the temperature is 30 degrees centigrade. The solid content of the cow dung is 15% and hydraulic retention time is 45 days. One cow produces 10 kg cow dung daily. So we have to find out the volume of the digester chamber. So I'll give you 5 minutes to solve this question. Just solve and write your answer, whatever you're getting. Well, so I'll give you 5 minutes.
Madam, I can't see the question properly. I think screen is cropped. Means zoom out the screen. Oh, yes.
So can you see the question now?
Yes, ma'am. Okay.
Okay.
So, Venkat, I'm going down, man.
Madam?
B is not the correct answer.
Yes, ma'am. Can you derive that?
So we'll see what is the solution. So C is the correct answer. We have given that there are 12 cow and each cow produces 10 kg of cow dung. So total amount of cow dung or total discharge produced will be 10 into 12. That will be 120 kg. And out of this, the solid content of cow dung is 15%. So total solid of fresh discharge will be 120 kg into 0.15, that is 18 kg of total solids is produced per day. Next is in digester, for optimally we provide 8% concentration of total solids to make the favorable conditions. So 8 kg of solid will be there in 100 kg of influent. So for 18 kg of solid, we will require 225 kg of influent. So as we know that the working volume of digesters can be calculated from the discharge into the hydraulic retention time. So here discharge is 225 kg influent per day, 225 into HRT is given as 45 days. So 220 into 45 will give us 10125 kg, and we will assume that 1000 kg of this is equals to 1 meter cube. So we will get the working volume of digester as 10.125 meter cube. But we have to find out the total volume of the digester. So, just give me. So let's see. So as we know from assumptions that working volume is around 80% of the total volume. So we can calculate the total volume as working volume divided by 0.8, which will give 10.125 divided by 0.8, and that will give the total volume as 12.65. So here we can see that we have working volume of 10.125 meter cube. We will divide it by 0.8 and we will get the total digester volume as 12.65 meter cube. So we have one more question. So it is based on previous question that in problem 9, we have to find the diameter of the digester. So it is a short question. So I'll give you 2 minutes. Just try to solve it and write your answer in the chat box. So the correct answer is A. So the digester diameter is related as total volume as D is 1.3078 V to the power of 1/3. We know V as 12.65. So we will put the value and we will calculate, and we will get the diameter of the digester as 3.047 meter. So today we have discussed the module of the week 6, lectures of the week 6, and we have discussed the previous year question of week 6. There will be 2 more discussion session on next week, on week 7, and then on week 8. And then finally the course will be over and you will have to appear for the exams who would have enrolled for the exam. So thank you so much for joining. If you have any doubt, you can
madam.
ask me.
I have. Yes, ma'am.
Okay.
Actually, when hall ticket will be released, ma'am?
I don't know about this. You can mail the NPTEL and you can ask from them.
Fine, ma'am. Okay, done. Thank you, madam.
Okay, thank you so much for joining. Thank you.